Hi, everybody. Welcome to calculus, pre-calculus today. Yesterday, I was showing you about what parametric equations are and how just to know the basics of them and to understand what it means when you see a parametric equation and how to do some stuff with them. Someone asked yesterday, why would we ever want to use parametric equations? And the answer to that is that they are one use of them is in physics. So I have here a warm-up question, and you've seen questions like this in Algebra 1, where they tell you, the height of a ball when you throw a ball in the air, it goes up, and then it comes back down. And if it's thrown, if it's up on a 128 foot tower to begin with, and you throw it up and it comes back down, the height of the ball would have some sort of a quadratic equation. So here's a warm-up question. If the height of this ball is determined by the equation h equals -16t squared plus 112t plus 128, how many seconds will it take for the ball to hit the ground, which is over there? So it's going to go up, and then it's going to go up and then down. Now, these numbers were chosen so that this would work out nicely. So everyone take a couple of minutes to think about that question. Okay, thanks for that. So here, the 16 is a factor of all the three numbers, and this works out, it factors nicely. And t equals 8 is the answer. This other answer doesn't really represent an answer because it's saying that like a second before the ball got thrown, assuming the ball came from, that it had been thrown from ground level, then a second before it's thrown, but that's not really what happened in this situation. The domain is from 0 on because the ball starts up over here. And that's a pretty famous question from algebra 1. Now, if the ball goes straight up and straight down, the graph, if I graph this equation, y equals -16x squared plus 112x plus 128, it makes this parabola. But the axes, this tells us nothing about how the ball is moving horizontally. Just want to make that clear. Like a lot of people look at this and say, oh, that means the ball follows this sort of path. But the ball does not necessarily follow that path, because this x-axis is representing time and the y-axis is representing height. So the ball might be going straight up and straight down. It would still make this graph. Or the ball might actually be going to the right as it goes up and down. Or for all we know, the ball is going to the left as it goes up and down. So I just want to make a point that this is not the actual like path of the ball. It's a representation of how the height of the ball changes over time. This T does not represent the horizontal displacement of the ball. The T represents how much time passed, and the H, the Y value, represents the height. So I just want to make that clear. Now, today we're going to see how parametric equations can be used to answer questions about predicting locations of projectiles, things that get sort of thrown to the right with some sort of initial force and an angle and an initial height. And it will remind you a lot of the game Angry Birds. When you're, and let's, you could type into the chat, and I see there's a couple of chats coming up, parametric. So in Angry Birds, now I'm not an expert at the Angry Birds game, so I know there's more decisions than this, like which bird you use might have various powers, but ignoring the whole point that, hold on, someone wants to, ignoring the whole like what bird you choose might have a impact on whether you achieve the goal of knocking down the structure. What are the two decisions that you have to make in Angry Bird when you're going to do a move? You could type it in. And that's right. By pulling the slingshot back, if I pull it back far, I'm affecting the force. The further back, the more force. But I also have to decide what angle to pull it back at, which angle with relation to the horizontal. So that we'll call theta, the angle, and this we'll call V0, because it's kind of implied that the further you pull it back, the faster the bird flies, the more power it has. I actually didn't even have this game on the iPad. I just downloaded it. And it doesn't even load up because it's a really old iPad, I guess. Give it a second. Angry Birds 2. I have an account of some sort. I didn't even know that. Anyone ever see the movie Angry Birds and the movie Angry Birds 2?
Yeah, first one was good. Second one was kind of whack.
There you go. I agree. The first one was, I thought it was pretty good, considering, they had to somehow get these birds into these slingshots. I liked it. I'll just do one. I don't play video games anymore because I played too many back in the 80s when Pac-Man and Donkey Kong were the big games. So I just don't try not to play video games. I shouldn't even be playing this one. Because once I start...
Yeah.
Wow, look at this. Okay, let's see how this works. Okay, good. They've got instructions. Okay, I know, I understand. Tutorial. Oops. Okay, little tutorial. Okay, can I play? How do I get a bird in there? Okay, well, this game isn't very fun if I can't have a bird.
The bird is already in.
He's in? Oh, so how come he's not flying?
It wants you to launch at that specific angle, like it wants you to follow that path.
Oh, I see. Wow. I'm pretty good. They said I had lost my swag when I gave up video games in 1991. So as you can see, very fun game and very addictive. I'm going to show you how we could analyze games like Angry Birds. And let me bring this up. Okay, and I'm going to start by showing you what this. So Angry Birds is the fun part, and now we look at what looks like a difficult equation. But let me explain what this equation means. Here's a little physics for you. When you launch a projectile with a force of v0 and an angle of theta, that force, and you might remember from last semester in pre-calculus, there's something called like component forces. It can be broken up into its horizontal component and its vertical component. And if I were to just make this another line here, that line, that vertical one, could also be the vertical component. And the lengths in this right triangle of these two sides are V0 is like the hypotenuse, sine theta, and the horizontal line, the length is V0 times cosine theta. So if theta is really close to 90, the vertical force is a lot, while the horizontal force is very small. If the angle is close to 0, the vertical component will be close to 0, and the horizontal component will be very close to V0. And that's why this second equation, oh, sorry, this is a parametric equation, but the bottom one is the easiest one to understand. V0 cosine theta is the horizontal force. And then if you multiply that by t, that will tell me what its horizontal position is at any time. And, you know, projectiles, like if you watch like a baseball, if it's hit like that, with ignoring wind resistance and things like that, if you just looked at like the shadow of the ball, that would go in a nice straight line. That would actually go at constant speed, which it's not really obvious, and with winds, it's not even true. But if we ignore like wind resistance and things like that, the horizontal, the thing moves horizontally at a constant rate. Again, it's not obvious, but I'm telling you it's true. And this equation encapsulates that. Whatever the horizontal velocity is in the beginning, it stays that way throughout, and that's why the horizontal location is V0 cosine theta times t. Now, for the height, which is y, it's a fact that gravity operates on Earth so that it's negative 16 feet per second squared is gravitational constant. So if we're using feet, which we are for our examples, this will always be negative 16 t squared. And the h0 represents the starting height. And this thing here, the v0 sine theta t, that is the vertical. That's sort of my my vertical component.
Could you explain what the negative 16t squared was again?
The negative 16t squared has to do with the fact that if you took a ball and it was really high and you just dropped it, it would go downward. So negative 16t squared kind of says that after 1 second, the thing will have fallen. If there was no extra push going up, after 1 second, it would fall 16 feet. But after 2 seconds, it would actually fall 60, it will have fallen 64 feet, negative 16 times 2 squared. So it's the effects of gravity. The negative 16 is how gravity makes the height get lower as time goes on. And we're always going to use negative 16. If you're using meters per second, you would use 4.9, because 4.9 meters is equal to 16 feet. But for our purposes, we're going to be using feet for our examples. A meter is 3.3 feet. So that's where this equation comes from. And now I'm going to show you the two scenarios. And today there's really just two questions to that shouldn't be taking so long. Loading image. I think loading up Angry Birds might have been a mistake, and this iPad I'm using is very old. What if I say skip? Okay, let me do a little bit. Let me get rid of Angry Birds. Sorry, everyone. Maybe I'll bring it back at the end. Let me also get rid of that. Got a lot of junk here. Okay, I'll try this again. Okay, so we have our two equations. Now, there are only two scenarios for today. The first one, I'm going to show you how we could use, and just to mention, notice how this is a parametric equation. And if you type this thing into the graphing calculator in parametric mode, it will also make, if I plug in numbers for theta and for t, it will make a graph like that also. But this time, the graph would not be representing time and height, but it would actually be representing x and y, horizontal, location, and vertical. So this is like more useful, whereas the other one really didn't tell us as much as it seemed. When you saw the parabola of the other one, the y equals with x squared, with y equals whatever t squared, that was this equation basically. That's just the height. But when I throw the x in there also, I get the actual shape of the graph. So let's look at the two scenarios. There's only 3 scenarios. We're going to learn 2 of them today and 1 tomorrow. So here is like a cannon instead of like an Angry Bird slingshot. And here's the given information. We are told H0 is 6.6. We are told the angle, which is 39 degrees. And we are told the initial velocity, V0, is 52.5. And this, and I sent you a link to this also, so let me show you where I got this from. Hold on, present, a Chrome tab. Okay, so here what we're looking at, this is kind of fun because it allows me to change the angle. And I can change the force by changing this initial speed. So that's how I change the two things. And kind of like Angry Birds, I can try to, to hit the target, something like that. Oh, I have a question for you. If I am trying to hit a target, how many correct ways are there to hit the target? And some people said 2, but it is actually more than 2. Nicholas is better than that, is better by saying a lot, because a lot is a lot. It's actually infinite. There are infinite number of ways if I have total flexibility of, because if I, for any given, let's say I'm trying to hit this, target over here, I could pick any angle I want, but I might have to do a lot of force. I think everyone was rooting for me to hit that. So maybe I'm not as good as I used to be back in my prime. This was not a game that was out when I retired from video games. Okay, got 1 star. I don't know if I can get, that's probably too much. Anyway, there are actually an infinite number of answers. And here, in this question though, they're asking, where is this thing going to land? Which is different than being told where the target is. So let me come back here and show you how we can calculate out. Presenting, stop presenting, present. Okay, back to calculation. So for any given angle, there is a V0 that will hit the target. If I tell you you must use this angle, there is a V0 that will hit the target. And if I tell you that, if I give you if I give you a V0, there's going to be an angle that would hit the target, assuming that it's possible. So, but basically, there's infinite ways of doing it. But this question does not have infinite answers, because this is asking a very specific question. It's asking, where will it land? How far? And that has a single answer. And I want to show you how to calculate that. We take our equation. Our equations are we want to basically know when is y equal to 0, because when y equals 0, the thing has landed. So the first thing we're going to do is we're going to figure out t for when does y equal 0. So remember this equation, y equals -16 t squared plus 52.5 sine 39 degrees times t plus 6.6. If you plug 0 in for y, well, you're going to need the quadratic formula to do that. So if you have your graphing calculator with you, why don't you go ahead and do the quadratic formula, and you'll calculate t. But t won't be the answer. Well, it will. It will be the answer to this question. Okay, did anyone work through the quadratic formula and come up with an answer for the value of t? Hmm, 10, I think it's too big. I see 1.57. Let's see if we get some agreement. This is the one that I got, 2.25. Although I tried to do it again on the graphing calculator and it didn't work. Let me bring up the graphing calculator for a second and see if I can bring that. Maybe see what I did wrong. So on the graphing calculator, window. So here's graphing calculator. I think if I'm doing this on the graphing calculator, which I have to find here, I think what I would do is take the so negative 16 is going to be the a value. I'll go store into a, and the b value is 52.5 times sine 39. I'll store that into b. And the c value is 6.6. And then finally, if I do alpha and y equals, I can make a nice fraction that way. So negative b plus square root. You might wonder plus and minus. There's two things. Maybe I should. I'll do both. B squared minus 4ac over 2a. That's going to be one of my answers, but that's. Let me go second enter and change that to a minus. Okay. And that's why 2.25 is the answer. Now that was only one of the questions though. The question then asked, what is the, where does it actually land? And type into the comments, how do you calculate out where it lands then? Like the horizontal displacement. Someone type in, how would you calculate it? That's right. You would multiply cosine 39 times 52.5 times 2.25, the horizontal displacement. And you would end up with an answer of 91.7, or about 91.8. Now, a fun thing to do is I could actually emulate this on that simulator, the thing that's the kind of the Angry Bird thing, but it's got a cannon and it's got like a David statue. Let's take a look, and we could actually check if we're right. Okay, let's see. Okay, here's that thing. Let me locate the actual screen of it. Okay, now this thing's in meters, but I will tell you that 6.6 feet is 2 meters. And 52.5 feet is the same thing as 16 meters, so that's 16 meters per second. And the viewing angle, well, that I don't have to convert. That's 39 degrees. And if this thing is right, and I put the target 91.7 feet, which is the same thing as 27.9 meters, and I shoot, let's take a look. Can I hit it perfectly with math? 3 stars. So as you can see, math, see, this is going to make Angry Birds for you like that much more fun. Okay, so that's our first question. And there are 3 scenarios. So I want to take you through the second scenario. And then we'll be done for today. I used to do all 3 scenarios in one day, but I think 2 scenarios is good for one day. Window. Okay, back to the iPad. Okay, now the second scenario is a little bit harder. So I'll show you how that one works. In the second scenario, in this one, we want to hit a target. Oh, that's strange. Okay, so here I have a projectile, and it's still 91.7 feet. I feel like something's wrong. That's all right. So, okay, so in this one, we are told that the angle must be 53 degrees. We have no choice there. And we want to hit a target like an Angry Birds that's 91.7 feet away. And then the question is, what should the initial velocity be? Take a second to think about this one. Like, how would you set it up? So
Wait, Mr. Rubenstein? Okay.
Leith, what's wrong, Leith?
Sorry. Are we gonna be doing daily attendance like on the Google Classroom anymore or no?
No, Leith.
Okay.
okay, hey everyone, I had to walk away for a second, but I'm back, and maybe you thought about this equation. So what you would have to do here in the second scenario, I see. This is, I'm not liking what I have here. Can I just look to see if I have another? No, I don't want that either. Okay, hold on one second. I see the issue. I'm going to change my scenario. So I'll make H0. We need to know 3 things. We need to know what the H0 is, and we need to know what the angle is. And we need to know what the horizontal displacement is going to be. And I see I had a mistake there. Sorry about all these mistakes. I've changed the lesson to make it agree with what I'm able to do on this simulator. 72.1 feet. Okay. Sorry. Those are the three pieces of given information. My angle, my H0, how high this cannon is, that angle there is the 53. But what's unknown is how much force in order to get the thing to land right on that bullseye. Now, this one's a little tricky. We actually start with the x equation. X equals V0, which we don't know, times cosine 53 t. And I'm going to substitute 72.1 in for x. I'm going to put parentheses around this cosine 53 so we don't think it's cosine of 53 t degrees. And there's not that much I can do here because I have two variables. So what I'm going to do is I'm going to divide both sides by t cosine 53 and get this V0 equals 72.1 times t cosine 53. So I have a relationship between V0 and t. Now, when it hits the target, not only is x going to be the 72.1, but since the target is on the ground, the y is going to be 0 at that moment. So we want y to be 0 at the same moment that x is 72.1. So what I'm going to do now is take the other equation, the y equation. 0 equals negative 16 t squared. I'm going to put it over here, plus. Now, this is the most confusing term, and I'm going to erase to give myself a little bit of room here. So we have 0 equals negative 16 t squared plus it's V0 sine theta t. But V0 we've worked out to be 72.1 times t cosine 53. And then we put the sine 53 and the t, and then finally plus 13.1. Does anyone see a way of cleaning up this mess, this middle term? Type in how much canceling can we do? The t's cancel, that's good. And you could do one other thing. Yes, sine over cosine is tan. So this turns into 0 equals negative 16t squared plus tan 50 plus 72.1 tan 53 plus 13.1. I'll go to a new page for that. So my equation is 0 equals negative 16t squared plus 72.1 tan 53 plus 13.1. And what's nice about this is it's actually not, I mean, technically it's a quadratic equation, but it's not one that needs the quadratic formula, because I get 16t squared equals 72.1 tan 53 plus 13.1. Divide both sides by 16 and take the square root of both sides. And take my word for it that if you type this carefully into the calculator, you would get 2.6 seconds. But 2.6 seconds isn't the answer yet. because the question was not how long does it take, but the question was how fast do we have to make our initial velocity. Type in to the chat, how do you figure out what the initial velocity is? And that's right. We use the other equation, the one with the x in it. So V0 is equal to 72.1 over cosine 53 times 2.6. And that will turn into 52.5. Oh, I see some people say 45.9. Anyone get with me 52.5?
45.9, yeah.
45.9. Let me check. Let me look at one thing here. 2.6. Yes, 45.9 is better. Okay, 45.9. 45.9 is the same thing as. Now, just to check that this actually works, I'm going to go over to the simulator with the Canon and put in those exact values, and we'll see if I am able to hit the target perfectly. Let's see, presenting, stop presenting, present now, a Chrome tab, projectile motion. Okay, so now we're back. Let me reset everything. So that 13.1, just so you know, was the same thing as 4 meters. The 53 degrees, that's still 53 degrees. The 72.1 is actually 27.9 meters. And we got an answer of 45.9, which is the same thing as 14, which is the same thing as 14. Let me make sure all these numbers are right. Yeah, 14, 53, 4, and 20. Oh, it wasn't 27.9. It was 21.96, about 22. I hope these numbers are all right. This will be very anticlimactic. 3, 2, 1. 3 stars. So as you can see, the math did work. It did predict what was going to happen. Now let me come back to the. And those are the 2 scenarios I wanted to show you for today. Let me pause the recording.